Hi, my name is Scott Simpson, and today we'll be talking about oxidation states. So in class we used oxidation states to figure out the transfer number of electrons or naming ionic compounds that have transition metals or other compounds that have varying oxidation states. So what an oxidation state is if you assume you have a completely ionic interaction between two elements that make up a compound, that's the charge of the element. So as an example, let's just look at sodium hydroxide, NaOH, where sodium is going to have a charge of +1 in this state. Actually, we'll write it down here. +1. Oxygen will have a -2. Hydrogen will have a +1. And the overall charge, if you add these up, ends up being 0. But this is assuming an ionic interaction or one at which the electrons are completely transferred. They're not shared like they are in a covalent interaction. Now, how did I know the oxidation states of these? Well, that you can figure out from a short list of rules, or oxidation state rules. So the very first rule is all group 1A elements have a +1 oxidation state. So group 1 is also known as the alkali metals. In terms of the alkali earth metals, or group 2A, they are all in a +2 state. 3, oxygen is usually in a -2 oxidation state. That changes if it's in a peroxide where you have two oxygens bound to one another. In that case, you have a -1 oxidation state. Rule 4. Any elements found by itself that's in a 0 oxidation state. So if we had sodium solid by itself, that would be in a 0 oxidation state. If we have sodium paired up with, let's say, an anion such as chlorine, then we would have it in a +1 state. The last rule has to deal with halogens. So fluorine is always -1. However, the other halogens, chlorine, bromine, iodine, their oxidation state can vary. Usually it's in a -1 state, but sometimes it can vary, mainly if something more electronegative is paired up with it. So other halogens, they're usually -1, but they can vary to other states. So let's see a couple of examples of this. So I'm just going to erase this. So let's look at a couple of examples. A, we'll do calcium sulfate. B, we'll do the phosphate anion. And C, let's do chlorine pentafluoride. So the way I do these oxidation state problems is I write the oxidation state of the element beneath it, and then if you consider all the elements together, what is the total charge on top? So for example, we have calcium. Calcium is usually in a +2 oxidation state. Since there's only one of them, that means that this total has a +2 up there. Now, the calcium is an ion as it is, but typically we do not write the +2 with it because one, it looks ugly, and two, when these get all paired up, the charge is neutralized. When we look at oxygen, oxygen's almost always in a -2 charge. Since we have 4 of them, that's going to be a -8 charge. Now sulfur, if you check the rules for sulfur, we didn't have any, so how are we going to figure that out? Well, we can figure it out from the total oxidation states of calcium and all of our oxygens. Calcium's in a +2 state, our oxygens in total get us to -8, so we need something to add to 2 and -8 to result in a 0. The answer to that would be +6. So our calcium's in a +6 state, our sulfur's in a our calcium's in a +2 state, our sulfur's in a +6 state, and our oxygen is in a -2 state. What about a system where we have a total charge? In that last one in A, all of the charges balanced out. In the case of B, we have an anion, the phosphate anion. How does that work out? Well, we have a -2 charge for each of our oxygens. Overall, that's going to again be a -8. Now, if you look, we have a charge on our compound here, at least on our anion. So whatever the charge on phosphorus is has to add to that -8 to result in a -3. The answer to that riddle, +5. So our phosphate's in a +5, our phosphorus is in a +5 oxidation state, our oxygen's in a -2 state again. In the case of chlorine pentafluoride, fluorine always has a -1 charge. I said chlorine could have a varying oxidation state. It usually is a -1, but it can vary. This is an example of it where we have a -1 charge for each of our fluorines. All of our fluorines together is a -5. Whatever the oxidation state of chlorine is has to balance out that -5. So we have a +5. So in this case, our chlorine is in a +5 oxidation state. Our fluorine is in a -1 oxidation state. So hopefully you can understand these rules. Just knowing where on the periodic table you're looking at. It actually is based off of the number of valence electrons that these compounds have, at least for group 1A and 2A and 7A, and for oxygen. But it gets a little trickier when you're looking at metals because their oxidation state might change a bit. An example that you can see where you have 2 varying oxidation states. Let's consider cobalt 2 chloride and cobalt 4 chloride. So these differ in the charge that the cobalt has and the number of chlorines that you would need to pair out that charge. So cobalt's in a 2+ state. We know that chlorine is going to be in a -1 state. So we need two chlorines to balance out the charge on the cobalt. So the molecular formula for cobalt 2 chloride would be CoCl2. In the case of cobalt 4, that's where we have a +4 charge on the cobalt. We again have a -1 charge on the chlorine. We know we're going to need 4 of these chlorines to balance out cobalt. So the formula for cobalt 4 chloride is CoCl4. So again, with transition metals, the oxidation state is important for the naming and figuring out the stoichiometry related to that cation in most cases, or that oxidation state. So hopefully you have a good idea about oxidation states now.